Okay, hello. We're continuing our exploration of the properties of a finite projective plane, and here's where we are. We have the finite projective plane axioms. Through any 2 points, there is exactly one line. It's dual axiom that any 2 distinct lines meet at exactly 1 point. And the axiom which sort of guarantees that there's some interesting stuff, which is FPP3. There exist 4 distinct points, no 3 of which are collinear. And all we've done really so far, I guess, is to show from this, we've shown FPP 3 prime, which is the dual of FPP3. I'm not going to write that down right now. And we proved that every line must have at least 3 points on it. Okay. And now it's time to get started with truly figuring out all of the properties that a finite projective plane must have. And the big theorem, which is going to come in the next video, requires a couple of lemmas. And Gossett calls these 2 lemmas lemma 8.4a and lemma 8.4b. It's pretty boring names. So we're going to prove lemma 8.4a now. Hopefully this will take about 10 minutes, and then you're going to prove lemma 8.4b for homework. And we'll go over it in the next video. Okay, here we go. Lemma 8.4a, what does it say? It says, let L be a line that contains exactly n plus 1 points. If P is any point that is not on L, then P must be on exactly n plus 1 distinct lines. Okay, so let's try to parse this, or perhaps we'll just start. Okay, so this is the theorem. So okay, so take line L with exactly n plus 1 points, and let's label those points with some kind of name, and we will have a picture going over here, which kind of explains what's going on. So here's my picture, I guess. Here is my line L. And what do I know about line L? It contains exactly n plus 1 points. So I think it's helpful to name those points. So let's name this point, P1, P2, P3, etc. And we'll go all the way out to the n plus first point. So this we will denote Pn plus 1. Okay. And so call the points P1, P2 to Pn plus 1. Okay, and if we're being very, very careful here, and we should be careful to note in our proof that, okay, these points are all distinct. That's what it means to have exactly n plus 1 points. N plus 1 distinct points is understood. And so what can I say about all these points? Well, I can say that P sub I is not P sub j for I not equal to j. This is the way that you make it clear that when a sort of identity and distinctness is under discussion, which it is in this kind of context, then we should be explicit that each of these points is understood to be distinct points, and that's how we note that. Okay. Have we even done anything yet? Not much. We're now in the second sentence. I'm still sort of digesting the assumptions for this theorem. P is any point that is not on L. Okay, so what is this point P? It's a point that is just not on L. Okay, so I'll just write that right now. So take P, which is not on L, and now I guess it's time to start doing something. What is the theorem? What's the content of this theorem? Then P must be on exactly n plus 1 distinct lines. Or more simply, there are exactly n plus 1 lines through P. And okay, it's pretty clear, I think, why this theorem is true. I have these n plus 1 points on line L. I have this point P, which is off of L, and through every 2 points there's a line, and so you just want to kind of go and connect each of these points to P, and each of those is a line, and we feel very strongly that it in fact is a different line. And then notice that the use of the word exactly here means we also need to explain why there are no more lines through P. So what we're going to show is that there are n plus 1 lines through P, and the answer is it's just what you would expect. It's the n plus 1 lines through each of the P sub I, and that there are no more. Okay, so, but to do this sort of very carefully, I will try to be sort of very explicit about my reasoning. Okay, well, one thing that is screamingly obvious from the picture, but has not yet been written anywhere on our work over here, where the real proof is happening, is that okay, I know all these P sub I are distinct from each other, but what about P? Can I say for sure that P is different from all of these points? Well, of course it is, right? And so we say, you know, since P is not on L by construction of P, or by assumption this point P is not on L, and each of the P sub I is on L, then I conclude that P is not P sub I. And in general, with these proofs, it's very important to establish this kind of at the outset. And I'm going to keep kind of like a running tab of sort of very important facts. So it's important that all the P sub I are distinct. It's important that P is not on L. It's important that we have established that P is different from all of those points. At least this is the style I find clear. Gossett is a little bit more casual. Okay, and now it comes time to reach for our axioms which allow us to create things. FEP2 says there must be a line through every one of these points, and so it's time to just make them, right? So I have this line through P and P1, I have this line through P and P2, I have this line through P and P3, etc., all the way over to P and P n plus 1. So okay, let's just cite that by FPP2, what does FPP2 say? FPP1 is what I meant to say. FPP1 says through any two distinct points are on exactly one line. And so that's why I sort of insisted that we note explicitly that P is in fact distinct from each of these P sub I. So by FPP1, we have lines, we have lines through P and each of the P sub I. And so really I'm going to basically be applying FPP1 like n plus 1 times. What should we call these lines? I think it is natural to call the line through P and P sub I to call it L sub I. Okay, so I hereby define the line through P and P1 to be L1, and this to be L2, and this to be L3, etc., all the way up to Ln plus 1. Okay, and this is the first moment at which you might think, okay, we're done. We've shown that there are n plus 1 lines through P. But no, in fact, we haven't really, because though our picture shows these lines as all being clearly different, there's nothing in our logical argument here that shows that in fact these lines are all different. And so that's what we need to show now. So I will now make my claim, and this is sort of the big claim. Claim these lines are all distinct. These lines are all distinct. And let's see, can I fit that down here in the bottom? I might be able to. How, or perhaps I'll fit it if I let myself go horizontally. Maybe I'll be able to fit it. So claim these lines are all distinct. These lines L sub I. All right, how are we going to do this? I think the natural thing to do is to suppose that they're equal and get a contradiction. So suppose that L sub I, contrary to common sense in our diagram, was equal to L sub j for I not equal to j. Why is this impossible? Being quite careful. Okay, so now we have to, if Li equals if Li and Lj are in fact the same line, then we'll just go to the definition of Li and Lj. What is Li? It's the intersection of P and P sub I, and Lj is the intersection of P and P sub j. And so what we have is P certainly is on this line. I'm going to call it L ij, because we've now supposed these lines are in fact the same line. P is on a line Lij, but P sub I is also on line ij, and P sub j is on line Lij. Okay, so what's wrong with that? And maybe it's worth it to throw in this idea here, right? That this is P sub I, and this is P sub j. I'm doing this in red, and there are two different points. What's the problem with there being a line through P and sort of both of them, so to speak? This would be this line Lij here, and I think the picture shows why this is sort of impossible, right? Because Pi and Pj are two distinct points, and now we have this line. Interesting. So we have these two distinct points, and now we have this line which goes through both of them. But that can't be, because we already have a line that goes through Pi and Pj, that's L. And so I realize I could have done this, and perhaps should have done this earlier, but I did not. My habit is when doing these proofs to sort of establish all facts as quickly as I can, but really actually here would have been the good moment to do it, although it's not wrong to do it now. At the immediate moment at which I introduced these L1, L2, L3, etc. lines, there was something I could have noted, which is that, of course, the picture suggests that they're different from line L. Do we have sufficient information to know that these lines are all different from line L? Yes, okay, right? Because since P is not on L, by the definition of P, or by assumption, and P is on, by construction, each of the L sub I, we conclude that in fact L is not any of the L sub I. So we're being very explicit in our logic, not reasoning based on the picture at all, using the picture only to guide us, sorry, not equal to. And so each of these lines which I introduced are in fact not equal to L. Well, that's important because that will help us now establish this contradiction that we're about to get, because yeah. Well, I don't just put this paper down. I don't need it. We're sort of already done, right? I have Pi and P sub j on this line Lij, but Pi and Pj are also on L. And so now I'm going to say, so to summarize, I have Pi on L. I have Pi on line Lj. I have Pj on L, and I have Pj on this line Lij. And this is a problem, because any two distinct points can be on exactly one line, and so this is a contradiction. This is a contradiction with, well, it's actually sort of a contradiction with both FPP1 and FPP2, but what you simply cannot have are two distinct lines meeting at two distinct lines meeting at two distinct points. And we know that Pi and Pj are distinct, and we know that L and Lij are distinct lines, and so it's impossible for those two distinct lines to meet at those two distinct points. So this is a contradiction. Okay, and that means, contradiction. That means, once again, you might think that we are done, because if these lines are all distinct from each other, and I have these n plus 1 lines, and they're all different, then I've shown that there are in fact n plus 1 lines through P, and maybe I'll even write that. So we have n plus 1 lines through P. But that's not quite good enough, because, and now I'll carve out some more space here, that's not quite good enough because I want to show that there are exactly n plus 1 lines through P, so I need to show that there are not any more. Okay, and to show that there are not any more, perhaps what I can do is just consider, you can sort of think of this by contradiction, but maybe it's easier to think of by just saying, okay, take some line through P. I will call this line M. Okay, so I don't know if you can see this, it's kind of in green, but I've just drawn a new line M through P. Okay, and what I want to argue is, depending on how you look at it, that either this line M can't exist, or I think it's smoother to just say that this line M must be one of the L sub i's. Okay, so take line M with P on M. In other words, imagine some arbitrary line that goes through P. Okay, well, what can I say about this line M? Well, first of all, I will establish that since P is on M, but that P is not on L, L is definitely different from M. And if L is different from M, then any two distinct lines meet at exactly one point. So, by FPP2, if L and M are distinct, then L must intersect M. Must intersect M at, say, I don't know, let's call this point Q or something. So what is this point Q? Q is a point which is on L, and Q is a point which is on M. Okay, but we know from the problem that there are precisely n plus 1 points on line L. So running out of space here, but Q must equal one of the p sub I, for some I. And so the only possibility is that, maybe I use it now a different letter. The only possibility for this line Q, for this point Q, well, what is Q again? It's the intersection of M with L, but it has to just be one of the p sub k. Okay, this is actually just too much detail. And so, what's kind of yeah, well, okay, so now, what do we want to say? Well, if P is on M, and P sub k is also on M, I'm going to squeeze this in. If P is on M, and P sub k is also on M, then what can we say about M? Well, then M must just be L sub k. In other words, given these 2 points, P and P sub k, that M goes through, well, what else goes through P and P sub k? Line LK does. And so if line LK is the line through P and PK, then M is just line LK. And what that means is that any line through P, in fact, must be one of the lines L1 through L sub n plus 1 that we've already been talking about. Okay, and so we sort of do this in 2 stages, right? We first introduce these n plus 1 lines, then we show that the lines are all distinct. So now we have these n plus 1 lines through P, and we show that there can't be any more lines through P, because any line, arbitrary line through P has to be one of the lines that we've already introduced, because it has to meet L somewhere, and there are only a certain number of points on L already. Okay, so it's a 2-step argument. All right, I think that was pretty clear. Good, bye.